Alright, now we're going to do problem number 4 of homework number 1. Specifically, problem number 4 reads, prove or disprove that if the probability of A is equal to the probability of B, which is also equal to the probability of the intersection of A and B, then A will equal B with probability of 1. We indicate as such up here that basically this is our given condition, and we wish to prove this term right here, which is basically the equivalent by definition of A equaling to B with probability of 1. So our final desire is to get this term, to prove if this term is correct or not. So the way we did it is that we actually broke down the problem into two parts. Technically, we could focus on this part, but just for sake of completeness, this more clearly shows the equivalence between terms. So I'm going to start with part 1 right here, which begins by basically breaking down the probability of A and probability of B. Okay, you can see here that the probability of A, all right, as we know, can be broken down in this way. That A can be termed as the intersection of A and the complement of beta. So what that's going to do is basically, if you think of a Venn diagram, the circle for A, this represents basically the circle for A, but like a chunk is chopped out of it to represent the intersection of A and B. And then we add the intersection of A and B. So basically, if you think of like a Venn diagram as being a circle, this term is more like the crescent, like so, like this term right here. And this term represents the chunk that's shared between A and B. So this can be broken down all over the place. It's like this is common. The other thing that we should know is that these two terms are mutually exclusive, which allows us to actually make this statement right here and break down the summation into the individual parts. So the probability of this plus the probability of that. We did the very same thing for the probability of B, beta. It's the same thing right here. The only difference is that we use the complement of A instead of the complement of B, which we used up here. Now, once we get these right here, using our given that A is equal to B, we can determine that, of course, like this minus that, because our equivalent is going to be equal to 0. So then we can substitute in these terms right here, which we show here. Okay, we substitute that term here and this term here. We play out the actual terms, cross out for commonality, see? And we determine this equation comes out right here, which breaks down that basically the probability of the intersection of A with the complement of B is equal to the probability of the intersection of the complement of A with B. Okay? What this term basically shows is that these two probabilities are equal to one another. Note, this particular proof right here doesn't tell you that both of them are 0 per se. They're just equal to one another. This right here, which is basically we use the actual terms right here, if we break those down, this will show us the actual values for these. Now, similarly right here, we can see how this term is going to be equal to this term right here. How do we show that? Basically, if you look at the, as I described up there, that this represents basically this crescent shape right here, excluding this little piece right there. Alright, this represents, like, in this case, beta, B. So another equivalent term that we could use is say, well, why can't we just say the probability of B, which is this whole thing, minus the probability of the intersection term? I mean, these two terms are equivalent to one another. We could do a similar breakdown right here with this interaction term, very similar to one another. All right. And furthermore, as I indicate, since our given shows that B and AB are equal to one another, A and AB are equal to one another, that the difference between the two in both cases is 0. Hence, what we show here is that these two terms are not only equal to one another, which we show here, but they're both equal to 0. Okay, and I say as much right here. Now, looking at both of these terms, we can discern that the two terms are mutually exclusive. Makes sense, right? Basically, if we had two circles, these terms basically chop out the portion which they intersect. So these are mutually exclusive terms. We need to say that because then we can actually say, well, the actual sum of the individual parts is equal to the probability of the sum as shown here. Now, why is that important? If we take all the data that we used up here for these terms, plus the fact that they are both equal to 0, we can break it down and show that this term, which is what we're trying to prove, is equal to the individual parts, which is basically 0 plus 0, and overall is equal to 0. Hence, we have proven that A is equal to B with a probability of 1.